You look at a skyscraper and you see power, you see permanence, you see the absolute pinnacle of human engineering achievement rising hundreds of feet into the sky, anchored to the earth with everything modern science has to offer. But here's what the glass and steel facade is hiding. Right now, at this precise moment, some of the most expensive and celebrated buildings in the United States are sinking. Not dramatically, not all at once, but millimeter by millimeter, month by month. These structures are descending into the soil beneath them, and the engineering failures driving that descent are costing building owners, city governments, and taxpayers billions of dollars that most Americans never hear about. And here is the part that should concern every single person watching this video right now. The same soil mechanics, the same load distribution failures, and the same engineering oversights that are sinking skyscrapers in San Francisco, New York, and Houston. They are operating beneath residential foundations, commercial strips, and municipal infrastructure in your city. The scale is different. The physics is identical. I am Engineer Vance, licensed forensic structural engineer. I have spent over 2 decades investigating structural failures at every scale, from residential slabs to high-rise foundations. And today, I am going to pull back the curtain on the sinking skyscraper crisis, explain the engineering science driving it, and show you exactly why it matters to every property owner in America, not just the ones with a penthouse view. Let me put the scale of this crisis into numbers that are impossible to ignore. The Millennium Tower in San Francisco, a 58-story luxury residential skyscraper that sold condominiums at prices exceeding $10 million, has sunk approximately 18 inches into the San Francisco Bay mud since its completion in 2008, and tilted approximately 22 inches off vertical at its roofline. The remediation program to stabilize that single building is projected to exceed $100 million, and that cost does not include the litigation, the diminished property values, or the infrastructure damage to adjacent streets and utilities. In Houston, Texas, which sits on one of the most complex and problematic subsidence environments in the entire United States, the Harris-Galveston Subsidence District has documented ground surface subsidence of up to 12 feet in certain areas over the past century. This movement is driven by a combination of groundwater extraction, hydrocarbon production, and the natural consolidation of thick Holocene clay deposits that underlie the entire Houston metropolitan area. Buildings constructed on that subsiding ground inherit every millimeter of that movement, and the structural consequences accumulate silently inside foundation systems, connection details, and building envelopes for decades before they become visible to anyone standing inside those buildings. In New York City, a 2023 study published in Science Journal documented that Manhattan Island is sinking at a rate of 1 to 2 millimeters per year under the combined weight of its buildings, and that certain areas of Lower Manhattan, sitting on poorly consolidated fill material placed in the 19th century, are subsiding at nearly twice that rate. The study calculated that the total weight of New York City's buildings exceeds 762 billion kilograms. That is a load that the geological substrate beneath that island was never evaluated to carry when those buildings were originally designed and permitted. To understand why skyscrapers sink, you have to understand what they are sitting on, and I mean that at a level of technical depth that goes far beyond what you will hear in any mainstream media coverage of this issue. The soil beneath every major American city is a stratified system of geological materials deposited over thousands to millions of years. In coastal cities like San Francisco, Miami, and New York, the upper soil profile is dominated by soft, compressible clays and organic deposits, materials with extremely high water content, low shear strength, and a critical property called consolidation potential. Consolidation is the process by which fine-grained soils, silts, and clays expel pore water from their void spaces under applied load, causing the soil mass to compress and the ground surface to subside. This process is governed by Terzaghis consolidation theory, the foundational framework of modern geotechnical engineering, which tells us that consolidation in thick clay deposits occurs over decades, not days. When a high-rise building applies hundreds of thousands of tons of load to a foundation system bearing on or above compressible clay layers, that clay begins a consolidation process that may not reach its primary consolidation endpoint for 20, 30, or 50 years after construction is complete. This is not a theoretical risk. This is a documented, measurable, and in many cases, a fully predictable engineering outcome that was either not adequately investigated or not adequately communicated to the parties responsible for the construction decisions. This is precisely what happened at the Millennium Tower. The building's original foundation system consisted of concrete friction piles, bearing in the dense sand layer approximately 60 feet below grade. What the original geotechnical investigation failed to adequately characterize was the magnitude of secondary compression, also called creep, that would occur in the thick bay mud deposits above and adjacent to the pile tips over the building's full service life. Secondary compression is the continued slow compression of clay soils that occurs even after primary consolidation is complete, driven by the rearrangement of soil particles under sustained stress. It is accounted for in the Geotechnical Engineering Standard ASCE 7-22 and referenced in IBC Section 1803 Geotechnical Investigation Requirements, but its long-term magnitude is notoriously difficult to predict with precision in thick, variable, soft soil deposits. The Governing Code for Foundation Design, IBC Section 1808, requires that foundation systems be designed to limit differential settlement to levels that do not impair the structural or functional performance of the building. What the Millennium Tower case exposed is that the gap between code minimum geotechnical investigation requirements and the actual geological complexity of soft urban soil environments is wide enough to swallow a 58-story building whole. Let me take you into the forensic details of the Millennium Tower case, because this is the most thoroughly documented and consequential foundation failure in American high-rise construction history, and the engineering lessons it contains are directly applicable to building foundations at every scale. The Millennium Tower was completed in 2008. It is a 58-story, 419-foot-tall reinforced concrete residential tower containing 419 luxury condominium units. The building was founded on a mat foundation system supported by approximately 950 concrete friction piles, driven to approximately 60 feet below grade into a dense sand layer known as the Colma Formation. The critical geotechnical fact that drove the subsequent failure is this. Bedrock in the vicinity of the Millennium Tower site lies approximately 250 to 300 feet below grade. The friction pile system terminating at 60 feet was bearing in a competent sand layer, but that sand layer itself sits above approximately 190 feet of soft to medium bay mud that was subject to ongoing consolidation under the building's 111 million pound gravity load. By 2016, 8 years after completion, the building had settled approximately 16 inches uniformly and had developed a differential tilt of approximately 2 inches at the base, translating to approximately 14 inches of lean at the roof level. Residents reported sticking doors, cracked drywall at floor-to-ceiling interfaces, and visible gaps at the building perimeter where the lobby floor had separated from the exterior plaza. My forensic analysis of the publicly available geotechnical data and structural monitoring records identifies 3 compounding engineering failures. The first was an inadequate geotechnical investigation scope. The original investigation characterized the Colma sand-bearing layer adequately, but did not perform sufficient laboratory consolidation testing on the full depth of bay mud to accurately project long-term secondary compression settlement. The second was foundation system selection. Friction piles, terminating at 60 feet, transferred the building load to a bearing layer that was itself subject to regional subsidence from adjacent construction, dewatering, and groundwater drawdown. End-bearing piles to bedrock at 250 feet would have isolated the building from that regional subsidence mechanism entirely. The third compounding factor was the excavation dewatering performed for the adjacent Transbay Transit Center construction beginning in 2010, which accelerated consolidation settlement in the bay mud deposits adjacent to the Millennium Tower by temporarily reducing pore water pressure in those layers. The remediation program approved in 2021 involves the installation of 18 new permanent steel pipe piles driven to bedrock at approximately 250 feet below grade, connected to the existing mat foundation through new concrete grade beams. The estimated remediation cost is $110 million. Individual condominium units that sold for between $2 and $10 million at completion had declined in market value by an estimated 25 to 40% by the time remediation was approved, a collective loss of hundreds of millions of dollars in residential property value. Whether you own a condominium in a high-rise, a unit in a mid-rise building, or a commercial property in an urban core, Here is the inspection protocol that engineer Vance uses when evaluating a structure for foundation settlement distress. The first external indicator to look for is any gap, step, or differential elevation change, where the building meets the surrounding hardscape, sidewalks, plazas, driveways, or parking structures. Settlement gaps at the building perimeter that exceed 1/4 inch are a documented threshold for engineering evaluation. The second external indicator is cracking in the exterior cladding system, particularly diagonal cracks emanating from the corners of window and door openings at the lower floors of the structure. Diagonal cracking at openings is the classic signature of differential settlement distortion in a building's structural frame, and it is one of the most reliable early warning signs available to a trained observer. The third external indicator is any visible lean or out-of-plumb condition in the building's vertical elements, something that requires a precision survey measurement, not a visual estimate, to document accurately. On the interior, the first indicator is doors and windows that have recently become progressively difficult to operate, particularly if the difficulty affects multiple units at similar floor levels simultaneously. This indicates that the structural frame is racking under differential settlement, distorting the door and window rough openings in a pattern that no amount of door hardware adjustment will resolve. The second interior indicator is diagonal cracking in drywall or plaster at the corners of openings, identical in pattern to the exterior cracking signature but visible from inside the unit. The third interior indicator is measurable floor slope. In a high-rise or mid-rise building, a floor slope exceeding 1/4 inch over 4 feet in any direction is a finding that requires structural engineering evaluation before any cosmetic repair is attempted. If you own property in a high-rise, mid-rise, or any urban building constructed on soft soil conditions, here's the action framework that protects your investment and your safety. The first level of response is monitoring. Any building in a soft soil urban environment should have an active settlement monitoring program in place, involving precision survey benchmarks installed at the building perimeter and measured at regular intervals, typically annually at minimum and quarterly for buildings showing active movement. The cost of a professional settlement survey for a mid-rise building runs between $1,500 and $4,500 per survey cycle. That monitoring cost is the cheapest and most effective form of early warning available, and the vast majority of building owners and HOA boards never commission it. The second level of response is geotechnical investigation. If monitoring reveals active settlement exceeding 2 millimeters per year, or if any of the visual indicators I described are present, a geotechnical investigation is mandatory. This involves soil borings adjacent to the building, laboratory consolidation testing on retrieved samples, and a geotechnical engineering report projecting total and differential settlement over the remaining building service life. For a mid-rise building, budget between $25,000 and $75,000 for a comprehensive investigation. That investment defines the entire remediation strategy, and without it, any repair work is engineering guesswork being billed at engineering prices. The third level of response is foundation remediation. Depending on investigation findings, remediation options include pile underpinning at $15,000 to $40,000 per pile location, compaction grouting at $50,000 to $250,000 depending on treatment volume, and jet grouting for soft clay environments at $100,000 to $500,000 for a mid-rise application. The sinking skyscraper crisis is not a story about exceptional engineering failures. It is a story about the limits of geotechnical knowledge, the pressure of production timelines, and the gap between code minimum requirements and geological reality. Those limits do not exist only beneath 58-story towers in San Francisco. They exist beneath every building in every city built on compressible soil, which includes most of the major urban centers in the United States. If you own property in an urban high-rise or mid-rise building, commission a settlement survey. Review your building's original geotechnical report. Know what your foundation is sitting on and what it is being asked to carry, because the physics does not care about the price you paid for that view. I am Engineer Vance. Protect your structure, protect your investment,